In this example, we're going to evaluate the effects of a wind production tax credit versus a fossil fuel generation tax. How do they work in the market? So let's start with a basic market, electricity market in the medium run, where quantity demanded is 100 minus P. The quantity supplied by the fossil fuel producers is just P, so that's their supply function. And then the quantity supplied by the wind producer is 10. It's a fixed supply. So find the equilibrium price and quantity in this market. To do that, we're going to get the total supply function. We're going to take QS equals QS fossil fuel plus QS wind, which is equal to 10 plus P. Okay, then we can find the equilibrium quantity by setting, we've graphed this function over here. We also have graphed the demand, so we can figure out the equilibrium. How? By getting the intersection between demand and supply. So we'll take QS equals QD, whoops, that should be a D. It's going to be 10 plus P equals 100 minus P. So we'll get 2P equals 90, and therefore P equals 45. And we know that wind is producing 10, so well, let's look at the total quantity produced. So P equals 45 at price of 45, the quantity demanded is 55, right? So QD equals 100 minus 45, and then we get QD equals 55. So this is equal to 55 and a price of 45. So Q supply wind equals 10. Q, because supply fossil fuel, is then going to be equal to 55 minus 10, which is 45. Now suppose there is a subsidy that causes 10 additional units of wind to be built, and let's resolve this problem. So now QS wind is 20. This means that the total supply function is P plus 20. Now let's resolve the problem, setting QS equal to QD. We'll get P plus 20 equals 100 minus P. So then we get 2P equals 80. And then P star is equal to 40. And Q star is then going to be equal to 100 minus 40, which is equal to 60. So of the 60 supplied, so here we go, Q star is equal to 60, P star is equal to 40, QS wind is equal to 20. We know that because the wind just supplies. It has a zero marginal cost. It's always going to be dispatched. The fossil fuel supply is then 40. So relative to the first part, without the subsidy, we have a higher quantity, total quantity. So the subsidy is actually increasing electricity consumption. We have a lower fossil fuel production, so we've reduced emissions, that's good, but a lower price. And we said that lower prices can actually hurt some renewable generators, so the subsidy might not be doing what, in effect, what we hope it would be doing. It might be pushing some higher renewable generators out of the market. Now suppose there is a $10 per megawatt hour production tax that is levied on the fossil fuel producers. And let's resolve the problem. So before we had the Q supply from the fossil fuel was equal to P, but now after the tax we have Q supply fossil fuel is equal to, it's going to take a little bit of a different functional form. It's P minus 10 if the price is greater than or equal to 10, and it's equal to 0 if the price is greater than, less than 10. Let me make that a little more clear. So we want to resolve the problem. To do this, we need to we get the total supply function, which is going to be QS fossil fuels plus QS wind. So our supply function is going to be QS is equal to 10 if P is less than 10. That's the wind production. So we went back to 10 for the wind producers. And P if P is greater than or equal to 10. So we can graph this. There's our demand function. And our supply function looks a little different now. This is at 10. So the question now is, where's this intersection? From the picture, it's kind of obvious that we can solve this problem by setting supply equal to demand, where supply is equal to P. So let's do that. QS equals QD, where supply is equal to P. So we're just really focusing on this part of the supply function here. Equals 100 minus P. So then we get 2P equals 100. So P star in this case is equal to 50. And Q star is then equal to 50 as well. Okay, of that, QS wind is 10, and that means that QS fossil fuel is equal to 40. So let's compare this to part A. What happened in relative to part A? So in part A, we had a price of 45, and we had a fossil fuel production of 55. Or sorry, fossil fuel production of 45, total production of 55. So let's go and compare that to what we just got. The price is now 50. It was 45 before, so price has gone up. The fossil fuel production has gone down. It was 45, now it's 40. So that's good. We've reduced our emissions. The tax is doing what we hoped it would do. It's reducing the fossil fuel production. It's increasing prices, and that, importantly, that increase in prices relative to the previous example, that increase in prices is good for renewable generation. That increase in prices is likely to lead to the construction of additional wind generation or some other form of renewables entering the market. It's incentivizing new entrants that are probably cleaner, because if you're a new entrant and you're dirty, you're going to pay that tax. Okay, finally, suppose there is still a $10 megawatt hour production tax, but an additional 5 megawatts of wind is constructed as a result of the tax. So this is kind of the long run, what happens after you've imposed the tax. We said that the prices increase with the tax, unlike the subsidy, and so this incentivizes further development of wind production, and so we've added 5 additional megawatts of wind production. This means this fossil fuel supply function is given by the same as it was before. If the price is greater than or equal to 10, it's P minus 10, and if it's less than 10, it's 0. The quantity supplied for wind is 15, that's this value here. So the supply function is going to be 15 if the price is 10, and P plus 5 if the price is greater than or equal to 10. That's because if the price is greater than or equal to 10, we're going to get that additional 5 units. So solve for the equilibrium quantities and prices. Again, doing so, we can now just focus on this section of the supply function in the demand function. So that's going to be P plus 5 equals 100 minus P over here. Solving this, we get P star equals 47.5, Q star equals 52.5, and of that, the supply from wind is 15. The supply from fossil fuel production is 37.5. So in the long run, this is pushing the fossil fuel production down even further. It's making the tax is making the market more competitive for the wind producers, which is going to push the fossil fuel production down further, which is reducing emissions even more. It's going to increase prices a bit, and that's what we hoped that the tax was going to do. It's going to reduce consumption. So consumption is declining a bit, but that's important because that's that's internalizing the social marginal cost of producing with the fossil fuels. So this, we're getting an even better outcome in the long run. So this basically is a comparison of a subsidy versus a tax. They each reduce emissions, but they ultimately have different effects. The subsidy is going to lower prices, but it's also going to lower emissions. It's going to lower prices and increase consumption, total consumption. It's going to be less of an incentive for additional renewable generation to come online. The tax is going to do the opposite. It's going to increase prices, creating more of an incentive for additional renewables to come online, and it's going to reduce emissions even further in the long run. So the tax is ultimately better than the subsidy.